All right, we're continuing on with solving trigonometric equations. I have 3 more examples I want to work through. And let's start with this one. So I'm solving secant squared of 3x equals 1 minus tangent squared of 3x on this interval from 0 to 2 pi. So kind of, if we take the previous example that we just did as sort of a clue, we saw that when we have a multiple of x as our angle, cosine of 2x, instead of just cosine of x, it was helpful to use this approach where we set up our interval as an inequality and then determine what the corresponding inequality would be for this 2x instead of just this x. I'd like to do something similar here. So even though I have 2 different trigonometric functions, we'll have to do something about that. But I'm going to wait on that. I'm going to start by dealing with this interval first. The angle in both of my trigonometric functions is a 3x. So I'd like to think, if x is between 0 and 2 pi, I'd like to think of where 3x is. Let me write this interval, again, in inequality notation. X is between 0 and 2 pi. Where would that put 3x? Well, if I multiply everything by 3, I'm going to get this. Okay? So now, instead of just searching through through 1 revolution around my unit circle, I'm looking through 3 revolutions around my unit circle, which is going to generate a longer list of solutions. Next thing I want to do is take this equation and see if I can figure out a way to get everything in terms of just 1 trigonometric function instead of 2. One thing you might recall is that your Pythagorean identity took on a couple of different forms. We had the most familiar one, cosine squared of x plus sine squared of x equals 1. But there's a couple other versions of that we derived in chapter 7, one of which said that secant squared of x is equal to 1 plus tangent squared of x. So if I were to rewrite this, I would need to write 1 plus tangent squared, and because my angle was 3x, I'd have to use the same angle here, 3x, equals 1 minus tangent squared of 3x. Cool. Okay, so how do we solve this? Let's try to simplify by getting all of my tangent squareds on the same side. Notice if I were to subtract 1 from both sides, each of these just cancel each other out. Then if I add the tangent squared over here, I get 2 tangent squared of 3x equals 0. And now I can divide by 2 and simply get tangent squared of 3x equals 0. So I'm still not quite there because I need tangent. I don't need tangent squared. But if I were to take square roots of both sides, I would get tangent of 3x equals. Now normally, remember, taking the square root of both sides, you'd put a plus or minus. But positive 0 and negative 0 are the same thing, just 0. So the plus or minus is unnecessary in this specific case. How am I going to find solutions now? Well, remember, we want solutions that go through 3 revolutions around our unit circle. When is tangent equal to 0? When the angle is equal to either 0 or pi within 1 revolution of my unit circle, I know that's where tangent is equal to 0. So it's not x though, it's 3x that we're plugging into that tangent function. So 3x can equal 0 or pi. But remember, that's only the first revolution around that unit circle. I have to keep moving through my unit circle to get through all 3 revolutions. So I can keep adding 2 pi to these previous answers. 0 plus 2 pi is 2 pi. Pi plus 2 pi is 3 pi. That carries me through that second revolution around my unit circle. One more revolution would get a 4 pi and a 5 pi in here. So that now I have 6 solutions for 3x. To solve for x, I just divide everything by 3. So I get 0 divided by 3, which is still 0. Then pi over 3, 2 pi over 3. 3 pi over 3 is just pi. 4 pi over 3. And 5 pi over 3. And again, notice after dividing by 3, all of these solutions are back to being in this interval, 1 revolution around that unit circle. So it worked out really nice. Okay, I'm going to leave my solution in this form. That's a totally valid way to write that. This next example on the outset might look really, really complicated. We see not only two different types of trigonometric functions, sine and cosine, but we're also seeing the two signs that are appearing here each have different angles. So they're not really like terms. There's no way to combine those. The cosines each have different angles. There's no way to combine those either. This seems kind of difficult and messy. But if you're thinking about your identities, the left-hand side of this might look really, really familiar. In fact, this reminds me of the difference formula for the sine function. So as a reminder, if I have sine of alpha minus beta, that's equal to sine of alpha cosine of beta minus sine of beta cosine of alpha. And that's precisely what we have here. In this case, alpha would be like the 2x. You see how here I'm taking sine of alpha and here I'm taking cosine of alpha, 2x and 2x. Beta would be like 4x. So I can actually I can use this in the reverse order and simplify the left-hand side of this equation by writing it as the sine of a difference. The left-hand side is the same thing as sine of 2x minus 4x. That is a lot nicer. This would be equal to root 2 over 2 still. What is 2x minus 4x? That would be negative 2x. Okay? Even though I could probably start working with what I have, let me go a little bit further. I know that sine is an odd function, which means negatives can be brought out. So let me do that. Negative sine of 2x equals root 2 over 2. Then let's divide both sides by negative 1 to get rid of the negative. Sine of 2x equals root 2 over 2. All right, cool. Now, I have that multiple of x here, like we've seen in the past couple of examples, but this time we're not solving on an interval. So I can't create that inequality notation that helped me through those previous two solutions. So instead, I'm going to just think about my unit circle and note that my angle is 2x. So what solutions might I be able to pull out of this? Sorry, I meant to make that a negative. We'll fix that. Where is sine equal to negative root 2 over 2? It happens in two places in our unit circle. Once in the third quadrant, once in the fourth quadrant. Specifically, it's going to happen when 2x, my angle, is equal to 5 pi over 4. And again, 7 pi over 4. Now remember here, we're looking for general solutions, not just one revolution around the unit circle. So I should be adding a 2 pi k to each of these. Okay? But it's not 2x that I want. It's x that I want. So let me solve each of these for x by dividing everything by 2. And I do mean everything. So if I divide both sides of this by 2, x will equal, what's 5 pi over 4 divided by 2? 5 pi over 8. I also need to divide this term by 2. Algebraically, that has to happen. All that's going to do is cancel this 2 out right here and give me plus pi k instead of 2 pi k. Similarly, over here, I'll get x equals 7 pi over 8 plus pi k. These would be my solutions. Okay? So a couple of neat, tricks there. One last equation, and then this should be a really solid, selection of examples to get you through the work in this section. Cosine of 2x equals cosine of x. There's a few different ways of thinking about this, but I want to use the identities that we've developed to help. First of all, even though these both involve a cosine, they are not like terms. In order to be like terms, not only would the trigonometric function that we're using have to be the same, but the angle inside of them would have to match. That's not the case here. I have an x here and a 2x here. They are not like terms, so I can't combine them. However, the 2x here can be put in, I can put this in terms of either a sine or a cosine of just x by using a double angle formula. Now, cosine of 2x has, again, 3 different double angle formulas that we encountered, and we, using kind of the strategy that we've already talked about, we can narrow those three down to just one that makes the most sense. Because I already have a cosine of x over here, I'm going to want everything to be in terms of cosine. And if you think through your double angle identities for the cosine of 2x here, two of those involve a sine squared somehow. I don't want to use those because I don't want to mix sines and cosines. I want to use the one double angle formula for cosine that that only uses cosines, and that's this one. Cosine of 2x is equal to 2 cosine squared of x minus 1. And that's equal to cosine of x. Okay? That is going to get me, that's going to get me somewhere. Because I have a cosine squared and a cosine here, still they're not like terms because one of them has an exponent that doesn't match this. So I'm thinking of this like a polynomial where I'd want to use the zero product property. Now I can subtract cosine from both sides. 2 cosine squared of x minus cosine, notice I'm putting that right here, minus 1 equals 0. And again, we're looking at a polynomial where the leading coefficient is not 1. So I'm going to use that diamond method technique again. 2 times negative 1 is negative 2. The coefficient on this term here, my linear term, is negative 1. So I write that. Now I need to multiply two numbers to make negative 2, but add up to negative 1. Negative 2 and positive 1 would work. Then I divide by my leading coefficient, which again in this case was a 2. If those can be simplified, we simplify. Okay, and then remember the denominator is going to be the coefficient on my variable, which in this case looks like cosine. So this represents 1 cosine of x minus 1, or just cosine of x minus 1. This represents 2 cosine of x plus 1. Okay, this is looking good because now what I want to do is set each of these independently equal to 0 and then solve. Cosine of x minus 1 equals 0, or 2 cosine of x plus 1 equals 0. On this side, if I add 1 to both sides, cosine of x is equal to 1. On this side, cosine of x after a couple of steps should equal negative 1/2. And I can get my solutions from here. Notice we're looking for general solutions again. It's not restricted to an interval. So cosine of x is equal to 1 in only one place, x equals 0, right? But then I also know that I'm going to add a 2 pi k to that because we're looking for general solutions. And I don't want to write 0 plus 2 pi k because the 0 is unnecessary. If I just write 2 pi k, that's the same thing, right? Adding a 0 to that doesn't change it. Here, when is cosine of x equal to 1/2? Well, negative 1/2. That would be in the second and third quadrants, specifically at 2 pi over 3 plus 2 pi k, general solution, and 4 pi over 3 plus 2 pi k. That would be my solution set. Okay, so one final comment I want to make before wrapping up this section in Chapter 9. You should notice, especially here where we're solving equations, how critical it is that you know your unit circle like the back of your hand. You should not need to look at a printout of your unit circle to come up with these. That you should be able to automatically go straight from an equation of either of these types to answers like this. This becomes even more critical as you work into calculus, and just, trigonometric functions are going to show up everywhere in pretty much all the math that you continue taking beyond this point, most likely. So it's really, really important that your unit circle is fully memorized by this point. Okay, that's it for Chapter 9.